seconds. Okay, welcome to the Physics 101, Lecture 1, and our first topic is units. So this is one of the important topic, but it is very simple. You can find all the lecture notes in the LMS. Also, you can look at my web page, but I haven't updated my web page now, so you can find the recent one in the LMS. Yes, for the course, we will have quizzes, and quizzes are 30%. Also, you will have the midterm exam, which will be 20%. And I will announce the quiz dates in the LMS, so you can check it in the course outline. And also you will have a lab participation 5%, lab exam 10%, and then you will have final exam 35%. And you must attend all labs and lab experiments. If you don't, you will take NG. Also, attendance is very important, so your attendance must be higher than 50%. As here you can see all the topics which we are going to study. So our first topic is units. So I'm going to start our lecture with the education is not the learning of facts, but it's rather the training of the mind to think, which Einstein said, because replacing homework with the home learning creates significant learning experiences that allow students to develop holistically and apply the curriculum to what they value. So students will require critical thinking skills in the future, which cannot be developed through a traditional approach to homework, according to the research. So now is the time to get creative, challenge students and rethink their approach to homework and also lecture notes. This will create valuable lifelong learning experience for future generations. So, and as Albert Einstein said, education is not the learning of facts, but it's rather the training of the mind to think. So, in this image might be showing any number of things. It might be a whirlpool in a tank of water, or perhaps a collage of paint and shiny bits done for art class. So without knowing the size of the object in the units we all recognize, such as meters or inches, it is difficult to know what we are looking at. In fact, this image shows the Whirlpool galaxy, which is about 60,000 light years in diameter, and it is about 6 times 10 to 17 kilometers across. So this image of the Whirlpool galaxy, which we examine in the here, galaxies are as immense as atoms are. The same laws of physics describe both of them, along with all the rest of the nature, as indication of the underlying unity in the universe. So we are going to use the same physics law for the galaxies, cosmology, and also for atoms. So the laws of the physics are surprisingly few, implying an underlying simplification to nature's apparent complexity. Yes, nature seems complexity, but if you understand it and if you apply the simple physics law, we can describe it easily. So in this course, you are going to learn about the laws of physics, and galaxies and atoms may seem far removed from your daily life. But as you begin to explore this broad-ranging subject, you may soon come to realize that physics plays a much larger role in your life than you first thought, so no matter your life goals or career choice. So what is the physics? Physics is the way to understanding of all natural phenomena. In physics, we try to understand physical phenomena at all scales, from the world of subatomic particles to the entire universe. Despite the breadth of the subject, the various subfields of physics share a common core. The same basic training in physics will prepare you to the work in any area of physics and the related areas of science and engineering. So in this section, we investigate the scope of physics, the scale of length, mass, and time over which the laws of physics have been shown to be applicable, and the process by which science in general and physics in particular operates together. So the forces that cause the Whirlpool galaxy, which I showed you before, to act as it does are thought to be the same force we contend here on Earth. Whether we are planning to send a rocket into the space or simply planning to raise the walls for a new home, the gravity that causes the stars of the Whirlpool galaxy to rotate and revolve is thought to be the same as what causes water to flow over hydroelectric dams here on Earth. So when you look at the stars, realize the forces out there are the same as the ones here on Earth. So through a study of physics, you may gain a greater understanding of the interconnections of everything we can see and know in the universe. Think now about all the technological devices you use on regular basis, such as computers, smartphones, global position systems, GPS, MP3 players, satellite radio might come to mind. Then think about the most exciting modern technologies you have heard about in the news, such as trains that levitate above tracks, invisibility cloaks that bend light around them, and microscopic robots that fight cancer cells in our bodies. All these groundbreaking advances commonplace are unbelievable and really on the principle of physics. Aside from playing a significant role in technology, professionals such as engineers, pilots, physicians, physical therapists, electricians, and computer programmers apply physics concepts in their daily work. For example, a pilot must understand how wind forces affect a flight path. A physical therapist must understand how the muscles in the body experience forces as they move and bend. As you will learn in the next sections, the principles of physics are propelling new, exciting technologies. And these principles are applied in a wide range of careers. So physics aims to understand the world around us at the most basic level. So, and its use of a small number of quantitative laws to do this, which can be useful to other fields pushing the performance boundaries of exciting technologies. Consider smartphone. Physics describes how electricity interacts with the various circuits inside the device. So this knowledge helps engineers select the appropriate material and circuit layout when building a smartphone. So knowledge of physics underlying these devices is required to shrink their size or increase their processing speed. So physics has many applications in the biological sciences or in engineers. So, and there are many branches of the science, as you can see here, for different scales. So on the microscopic level, it helps describe the properties of cells and their environments. On the macroscopic level, it explains the heat, work, and power associated with the human body and its various organ systems. Physics is involved in medical diagnostics such as radiographs, magnetic resonance imaging, and ultrasonic blood flow measurements. And medical therapy sometimes involves physics directly. For example, radiotherapy uses ionizing radiation, And physics also explains sensor phenomena, such as how musical instruments make sound, how the eye detects colors, and how lasers transmit information. It is not necessary to study all application of physics formally. What is most useful is knowing the basic laws of physics and developing skill in analytic methods for applying them. Furthermore, physics retains the most basic aspect of science, so it is used by all sciences, and the study of physics make other sciences easier to understand. So, physics deal with the nature and properties of the matter and energy, and the laws of physics governs everything in the observable universe at all measurable scales of length, mass, and time. So, physics, the most fundamental physical science, and is considered with the fundamental principles of the universe. It is the foundation upon which other sciences, astronomy, biology, chemistry, and geology are based. It is also the basis of a large number of engineering applications. The beauty of physics lies in the simplification of its fundamental principles, and in the manner which just a small number of concepts and models can alter and expand our view of the world around us. So you can divide the physics into 6 main areas. One of them is classical mechanics, which concern the motion of an object that are large relative to the atoms and move at speeds much slower than the speed of light, as you see in this table. And another area is relativity, a theory describing objects moving at any speed, even speed approaching the speed of light. Okay. Another one is thermodynamics. It is not here. Thermodynamics dealing with heat, temperature, and the statistical behavior of system with large number of particles. And another one is electromagnetism, concerning electricity, magnetism, and electromagnetic fields. Another one is optic, study of the behavior of light and its interaction with material. And the other area is quantum mechanics, a collection of theories connecting the behavior of matter at the submicroscopic level to the macroscopic observations. So if you want to understand the subatomic particles like electron, proton, quarks, you must know quantum mechanics. So, and if you want to understand relativistic quantum particles, you must know quantum field theory. So the disciplines of mechanics and electromagnetism are basic to all other branches of classical mechanics and classical physics, and also modern physics. So modern physics begin from 18th century. So the first part of these books deal with the classical mechanics, sometimes referred as a Newtonian mechanics or simply mechanics. So many principles and models used to understand mechanics systems retain their importance in theories of other areas of physics. Therefore, the classical mechanics is of vital importance to students from all disciplines. But you know that the physics is based on experimental observation and quantitative measurements, and we are using mathematics as a tool. So, Physics 101 is based on classical mechanics, which deal with the motion of objects, and the classical mechanics is concerned the motion of objects that are large relative to the atoms and move at speeds much slower than the speed of light. So for everything you can see around you. Yes, for this chapter, we are going to study units, measuring things, unit conservation, and SAI units, standard units, and dimensional analysis. To describe natural phenomena, we must make measurement of various aspects of nature. So without making measurement, you cannot say anything physical. So each measurement is associated with a physical quantity, such as the length of an object. So the laws of physics are expressed as mathematical relationship among physical quantities we will introduce and discuss through this lecture. So, for example, how tall is Ming Yao? How about his weight? So you can say that his height is 2.29 meter or 7 feet 6 inch. You can say also his weight is 141 kilogram or 310 pounds. So you can use different units to express it. But if you don't use the unit, the number only cannot define any physical quantity. So thickness is 10, has no physical meaning because there is no unit. So always you must use number plus unit. Yes. Without unit, it isn't physical. And also if you don't write the unit in the exam, you will lose point. In mechanics, there are three fundamental quantities, which are length, mass, and time. All other quantities in mechanics can be expressed in terms of these three. And also another quantity which you can derive from these basic quantities like is speed. So you can use distance and time to derive speed. We say these quantities as a basic quantity. So what are they? Length, mass, and time. So you can define other ones in terms of this. So measurements of physical quantities are expressed in terms of units. If we are to report the result of measurement to someone who wishes to reproduce this measurement, a standard must be defined. So measurement standard used by different people in different places throughout the universe must yield the same result. To measure system of units are used in the world. One of them is SI units for the French system international the units, also known as the metric system, and the other one is English units, also known as the customary or imperial system. English units were historically used in nations once ruled by the British Empire and are still widely used in the United States and also in Cyprus. English units may also be referred to as the foot-pound-second system, as opposed to the centimeter-gram-second system. In addition, standards used for measurement must not change with the time. In 1960, an international committee established a set of standards for the fundamental quantities of science, and it is called the SAI, Sistema International, and its fundamental units of length, mass, and time are meters, kilometer, and second, respectively. Here, for the SAI units, what we are going to use for length, meter. For mass, we are going to use kilogram, and for time, we must use second. And also, there are other fundamental or basic quantities. What are they? Which we are going to study in the physics 102. Electric current, and for the electric current, we are using ampere. For thermodynamic temperature, you are going to use Kelvin. For luminous intensity, you must use candela. And for amount of substance, you must use mole. Yes. Another important thing is, why should we care about the units? So in the history of human, because of the people are using different units, what happens? Mars Polar Lander and Deep Space 2 were lost at arrival on the Mars. And also, there are other disasters happens in the history. For example, some of the planes fall down because of they use different units. From here, one company using the British system and another company using the SAI American SAI system. So after that, the electronic system not working properly, and they lost this lander in space. So the peer review preliminary finding indicated one team used English units, inch, feet, and pounds, and while the other used metric units for a K spacecraft operation. So how can you define? So it is important to use same units. That's why we define SAI units. And for the length, we are going to use meter. So let's look at that. What is the meter? The meter is the length of a path traveled by light in a vacuum during a time interval of 1 over this number of 1 second. So we can identify length as the distance between 2 points in space. In 1120, the King of England decreed that the standard of length in his country would be named the yard, and would be precisely equal to the distance from the tip of his nose to the end of his outreach arm. Similarly, the original standard for the foot adopted by the French was the length of the royal foot of King Louis. King Louis 19. Neither of this standard is constant in time. When a new king took the throne, length measurements changed. So the French standard prevailed until 1799, when the legal standard of length in France became the meter, defined as 1/10,000,000th of the distance from the equator to the North Pole along one vertical longitudinal line that passes through the Paris. Notice that this value is an Earth-based standard that doesn't satisfy the requirement that it can be used throughout the universe. So in October 1983, however, the meter was redefined as the distance traveled by light in vacuum during a time interval of 1 over this number of 1 second. So this definition is valid in all universe. And similarly, they define the time and they define the second. So before 1967, the standard of time was defined in terms of the mean solar day. A solar day is the time interval between successive appearance of the sun at the highest point it reached in the sky each day. The fundamental unit of a second was defined as 1 over 60 times 1 over 60 times 1 over 24 of a mean solar day. This definition is based on the rotation of one planet, the Earth. Therefore, this motion doesn't provide a time standard that is universal. So that in 1967, The second was redefined to take advantage of high precision attainable in a device known as atomic clock, as you see in the figure, which measures the vibration of the cesium atom. There's the atom, and they use this cesium atom for the vibrations. And 1 second is now defined as in terms of an atomic clock time taking for this amount of oscillation of the light emitted by a cesium atom. So this is the period of vibration of radiation from the cesium 133. So defining unit precisely in a science, it is important. For example, they use the GPS around the Earth. So this clock will neither gain nor lose a second in 20 million years. So it is very important. So these atomic clocks with GPS now you can use it in everywhere in the universe. So similarly, they define the kilogram. So kilogram is the mass of a specific platinum-iridium alloy and kept at International Bureau of Weights and Measures near Paris, and also the copies are kept in many other countries. So the Yao Ming is 140, which is equivalent to weight of 141 pieces of the alloy cylinder, as you see in the figure. And in the universe, there are different scales of the length. For example, the diameter of the proton is 10 to minus 15 meter. But if the of Earth is 10 to 7 meter, and the largest length is the distance of the edge of the observable universe, which is the 10 to 26 meter. On the other hand, for the masses, the lightest object is the mass of electron, which is 10 to minus 30 kilogram. And the heaviest object is the upper limit on a mass of the known universe, which is the 10 to 53 kilogram. So the range, the scale is very high. So for the time is the shortest time is the mean lifetime of very unstable nucleus. So because it is decaying in 10 to minus 22 seconds, and the age of the universe is 10 to 18 seconds. And you can see the order of the of length, mass, and time in this table. Also, using the prefixes for SI units are important. So what we are going to use? So SI units are part of the metric system, which is convenient for scientific and engineering calculation because the units are categorized by factors of 10. For example, for hexa, it is 10 to 18, and we use E. For peta, it is 10 to 15, and P. For tera, nowadays we are using terabytes, 10 to 12, we use T, and 10 to 9 is giga, shown by G. 10 to 6 is mega, we show by M. 10 to 3 is kilo, we show by K, and 10 to 2 is hecto, we show by H, and 1 is deca, dA. So how can you convert from, for example, meter to kilometer? So from conversion to meter to kilometer, kilo is 10 to 3. So 3000 meter is equal to 3 times 1000 meter. So 1000 is 10 to 3. You can write it as a 10 to 3. So this 10 to 3 is equal to kilo. So you can write it 3 kilometer. Similarly, you can write giga, mega, and kilo. And what is the 1 141 kilogram in gram. So how can you write it? You can write it like that. Let's write it. So it is equal to 141 times kilo means 10 to 3. 10 to 3 gram. Okay, it is very simple. Also, similarly, you can write for byte and megabyte. 1 gigabyte is equal to how many bytes? Giga is 10 to 9. Okay. And it is equal to how many megabyte? 10 to here you can see also the prefix for the small units. For example, for deci, you use 10 to minus 1. Centi means 10 to minus 2. Milli is 10 to minus 3. Micro is 10 to minus 6. Nano is 10 to minus 9. Pico is 10 to minus 12. Femto is 10 to minus 15. And atto is 10 to 18. So these yellow colors are important. So you can similarly convert them to these small prefixes. For example, you can convert it to milli by multiplying 10 to minus 3. So 0.001 is equal to 10 to minus 3, so it is equal to 1 milli. So 3 centimeter is equal to how millimeter? You can convert them. So they are simple. So there are many examples. We are going to solve the difficult one. So you can try to solve them. So here also you can see both of them for largest one and smallest one. So another important thing in the physics are what? Derived quantities. So what is the derived quantities? So you can use the basic quantities to derive them. For example, you can derive area, speed, volume, density. Area is equal to length times length. So the unit will be meter times meter, meter square. Also, volume is the derived quantity. Length times length times length. So the unit will be m cube. Also, speed is derived quantity because you derive it by using length over time. So length is meter, time is second, so meter over second. So density is also derived quantity. Use mass over volume. So mass is kilogram, volume is meter cube. So here there's a one simple example for derived quantities. In 2008 Olympic game, Usain Bolt sets world record at 9.69 seconds in men's 100-meter final. What is his average speed? So how can you calculate it? His average speed is 100 meter over 9.69 seconds. And
should we divide the numbers? 100 over 9.69, right?
Yeah, this one, so let's write it. So speed is equal to here length over time. So length is 100 meter. 100 meter and time is in 9.69 seconds. So you divide them and you can find its speed in terms of meter per second. So speed is derived quantity as you can see here. And there are also other unit system which I mentioned before. like USA customer system, foods like second, and centimeter gram second system. So, but in the science, in this course, we are going to use SAI units. So it is often necessary to convert from one unit to the another. For example, if you are reading a European cookbook or some quantities may be expressed in a unit of liters and you need to convert them to cups. Or perhaps you are reading walking directions from one location to another and you are interested in how many miles you will be walking. So in this case, you may need to convert units of feet or meters to the miles. So let's consider a simple example of how to convert units. So 1 mile is equal to 1,609 meter, which is equal to 1.609 kilometer, because kilo means 10 to 3. So 1 meter is equal to 39.37 inch. So you don't need to memorize these conversions we are going to give you. Okay, so 1 pound is 0.465 kilogram, and 1 day is 24 hours. 1 feet is 30.48 centimeter, and 1 inch is 2.0 meter. So let's look at one simple example. Yes. So let's consider a simple example of how to convert units. Suppose we want to convert 80 meter to the kilometer. The first thing to do is to list units you have and units to which you want to convert. In this case, we have units in meters and we want to convert to kilometers. So how can you convert to kilometers? Next, we need to determine a conversion factor relating meters to kilometer. A conversion factor is a ratio that expresses how many of one unit are equal to another unit. For example, there are 12 inch in 1 feet, 1,609 meter in 1 mile, 100 centimeter in 1 meter, 60 seconds in 1 minute, and so on. So you can see that in the table. For more complete list of conversion factors, yes, look at the table, and also we are going to give you in the exam. In this case, we know that there are 1,000 meters in 1 kilometer. Now we can set up our unit conversion. We write the units we have and then multiply them by conversion factor so the units cancel out. So you want to convert 80 meter to the kilometer. So first write 80 meter, then times 1 kilometer over 1,000 meter. So here you can see easily that meters are cancelled to each other, and then when you make this calculation, you can find that it is automatically converted to kilometer. So it is equal to 0.080 kilometer. So the first thing, yes, you want to write the conversion factor and multiply. You can do also for this density. The density of iron is 7.86 gram over centimeter cube. So under standard condition, convert this to kilogram over meter cube. Here first you must convert gram to kilogram, and then centimeter to the meter, and then centimeter cube to meter cube. So we need to convert grams to kilogram and cubic centimeter to cubic meter. You must be careful about here. The conversion factor we need are 1 kilogram is 10 to 3 gram, and 1 centimeter is 10 to minus 2 meter. However, here we are dealing with cubic centimeter, so cubic means centimeter times centimeter times centimeter. So we have to use the second conversion factor 3 times. This idea is still to multiply by the conversion factor in such way that they cancel the units we want to get rid of and introduce units we want to keep. So here you write 7.86 gram over centimeter cube. Then you must to convert it by this one, because 1 kilogram is equal to 10 to 3 gram. So when you divide them, okay, here I show you. So if 1 kilogram is equal to 10 to 3 gram, you divide it. So 1 kilogram is equal to 10 to 3 gram, which is equal to 1. Okay. So if you multiply something with 1, nothing has changed. Okay. So that's why we multiply by this conversion factor. So here you can see that grams are cancelled to each other. So you convert it to the kilogram. But you need to also convert centimeter cube to the meter cube. This time you are going to use 1 centimeter is equal to 10 to minus 2 meter. So centimeter over 10 to minus 2 meter. But you must take also cube for both of them. When you take the cube of both of them, centimeter cube is cancelled with centimeter cube. And at the end, you must make this simple calculation. So 7.86 over 10 to 3 times 10 to minus 6. Why it is minus 6? Because 10 to minus 2 times 3 is 10 to minus 6. And this calculation is equal to 7.86 times 10 to 3 kilogram over meter cube. So this is very simple. Oops.
Excuse.
Yes.
Could you just make it into a fraction and multiply it by the given number instead of going the whole way, or this is the compulsory method?
Yes, you can do what you want, but here, if you do in this way, you can see your mistakes easily.
Okay.
Yes, for the simple case, for example, for you converted, for example, 80 meter to kilometer, it is simple. You can do it easily. But for the complicated cases, if you write them step by step, it is better. Yes, another question.
Yes, I wanted to ask you, minus 2 to the power of 3, is it minus 8? Not minus 6, right?
10 to minus 2 over 3 is, yes, 10 to minus 6.
Minus 2 to the power of 3, is it minus 8?
No, where is minus 8? 10 to minus 2 times 3. Because it's like that. I show you. 10 to 10 to minus 2 over 3. Okay. It is equal to what? 10 to minus 2 times 10 to minus 2 times 10 to minus 2. So it is equal to 10 to, you must add them. Make a summation 10 to minus 6.
Okay. We should add them. I got it. Thank you. Thank you so much.
Yes, another question. Okay, let's go. And let's look at this example. Is he speeding? On an interstate highway in a rural region of Wyoming, a car is traveling at a speed of 38 meters per second. Is the driver exceeding the speed limit of 75 miles per hour? In some cases, mile per hour is also writing as mph. Okay, this is also mile per hour. So how can you do it? You must convert meters to the miles and seconds to the hours. So first you write 38 meter over second. Then you must multiply by conversion factor. So conversion factor is 1 mile is equal to 1 mile is equal to 1609 meter, so that you can divide 1 mile to 1609 meter, and meters are cancelled to each other, and you convert it to the mile. After that, you must convert second to the hour. You know that 1 minute is equal to 60 seconds, and 1 hour equal to what? 60 minutes. Okay, So 60 seconds over 1 minute. Why we write second up? Because you want to cancel second with this second. This is down, this is up, so they cancel each other. Then you multiply by 60 minutes over 1 hour. Also, you can use directly that 1 hour is equal to 3600 seconds. Okay, you can, if you want, you can use directly this one. So 3600 seconds over 1 hour. And here at the end, minutes also cancel to each other, and you are going to find 85 miles per hour. So the driver is indeed exceeding the speed limit and should slow down because this speed is larger than 7 speed limit mile per hour. Okay, it is larger than, so it should slow down. And the next part, they asked that what if the driver were from outside the United States and is familiar with the speed measured in kilometers per hour? What is the speed of the car in kilometers per hour? So now let's convert it to the kilometer per hour. So first write 85 miles per hour, then use this conversion, but here you must use kilometer 1. For changing kilometer, you must multiply by 10 to minus 3. So 1.609 times 10 to 3 kilometer. Okay, because when you multiply by, and it is also equal to what? 1609 times 10 to minus 3 kilometer. Okay, it is same. Here is minus, but here I put dot and put 3. Okay, so you multiply 85 with 1.609 kilometer over 1 mile, and miles are cancelled to each other, and you convert it to the kilometer. Another important thing is the dimensions, units, and equations. So the dimension of any physical quantity expresses its dependence on the base quantities as product of symbols or powers of symbols. So they are representing the base quantities. For example, a measurement of length is said to have dimension L. A measurement of mass has dimension M, or a measurement of time has a dimension T. Like units, the dimensions obey the rules of algebra. Thus, the area is the product of two lengths, and so has dimension is L squared, or length squared. So similarly, volume is the product of three lengths and has the dimensions L over 3, or length cubed. Speed has dimension length over time, so L over T. Physicists often use square brackets around the symbol for a physical quantity to represent the dimensions of that quantity. So you can see it here. So we use bracket of A, which is for the dimensions. So dimension of area is L square and unit is M square. For acceleration, dimension is length over time square. So let's look at a simple example for it. So the importance of the concept of dimension arises from the fact that any mathematical equation relating the physical quantity must be dimensional consistent, which means that the equation must obey the following rules. Every term in an expression must have the same dimensions. It doesn't make sense to add or subtract quantities of different dimensions. Think of the old saying, you can't add apples and oranges. In particular, the expression on each side of the quantities in an equation must have the same dimension. So if the left side is length right side must be length. If left side is time square, right side of the equation must be also time square. So the arguments of any of the standard mathematical functions, such as trigonometric functions, such as sine and cosine, logarithms or exponential functions that appear in the equation must be dimensionless. So these functions require pure numbers as inputs and give pure numbers as outputs. So if either of these rules is violated, any equation is not dimensionally consistent and cannot possibly be correct statement of physical law. So the simple fact can be used to check for typos or algebra mistakes, to help remember the various laws of physics, and even to suggest the form that new laws of physics might be taken. So this last use of dimension is beyond the scope of this course, but it is something you will undoubtedly learn later in your academic career. So here, let's look at this example. Show that the expression v is equal to at, where v represents speed and a acceleration and t an instant of time, is dimensionally correct. So identify the dimensions of v. So what is the v? V is speed, so length over time. Okay, what is the a? A is acceleration, so length over time square. Here in this equation, there is a t. There is a t. So you can put t. So one t and another t is cancelled to each other. So at the end, you can find length over time. So we know that v is length over time. So it is same. So it is correct. So we can say that this equation is dimensionally correct because we have the same dimensions on both sides. Another one is, if A, B, and C have unit of meters, what is the unit of S? So if A have, both of them are same units, what are the units of S? S will be also in meters. So unit of S is also in length. Okay. So another question, let's write it. So unit of S is length. So if A, B, and C have the unit of meters, what is the unit of S? Which is equal to A plus B. Okay, so length plus length is, nothing is changed. So length plus length is also equal length. Okay, so unit is also will be length. Okay, so length plus length is, it will be length, nothing has changed. So what is the unit of S if 2a plus b times b? Here there is a multiplication. So inside the parenthesis, nothing is changed because there's a summation. So here is length, but when you multiply by length, it becomes length square. Here there's a cube, so what happens? It becomes length cube over length. It is equal to length square. The unit of the S is length square. And in the next one, there's a summation inside the parenthesis, so it is here is length square. Inside the parenthesis is like a square root, so length 1/2 over 9. 9 is not important because it's a number, it doesn't change the unit. C square is L square. So at the end, it will be equal to 1 over length 1 over 2. So the unit of this term of the S is 1 over length square root. Okay.
Yes, teacher, can you repeat the last one? I didn't get it.
Okay, for the last one, inside the parenthesis, there's a 3a plus 4b. Okay, so the multiplication with number not changing the unit of length units, and also summation is not changing. So the here is what directly you can write length. Okay, and it is over 9c square. 9 is not important here, and c square is length square, so you can write over length square. After that, what happens? Here is length 1 over 2, here is length square, but here, yes, we make mistake. Let's write it. Oops. Let's write it openly. Let's write it openly. Length 1 over 2. Okay. Plus, but here it is over. Okay. So if you write over, you can write it like that. Minus 2. Okay, it is equal to like that. So it is equal to what? Length 2 times 2 is 4. So 1 minus 4 over 2. It is equal to L minus 3 over 2. Okay? Don't forget to put brackets. Okay, so this is the unit of the S. Do you understand? So you must be very careful also when making algebraic calculations. Yes. There are also other examples. Yes, you can do them in the home. It is similar. Also, the solutions are here for A and B, and for C, it is homework. You can try to do yourself. Another important thing is the unit conversion, as I said. How can you convert mile to, for example, centimeter? By using this conversion factor. So you must use this one. Okay. 1 mile is equal to 5,280 feet. 1 feet is 12 inch. 1 inch is 2.54 centimeter. To convert this, you must first write 2.3 miles over 1. And you must first convert it to the feet, because they give you this conversion factor. So times 5,280 feet over 1 mile. After that, the miles are cancelled to each other. You have a feet. So you must convert feet to inch. So 12 inch over 1 feet. Now feet are cancelled to each other. After that, 1 inch is 2.54 centimeter. So inch are cancelled to each other. So at the end, you can find it in terms of centimeter. So using this way is easy, and also you can see easily your mistake. Okay, today what we learn? We learn the what is the physics, what is the scope of the physics, and the units, and how can you make your unit conversions. And also what we learn the very important things, because in all of your career you must always use units, because without units number has no physical meaning. So tomorrow I'm going to continue with solving some more examples. So today I think it is enough. So have you got any question?
I have a question, sir.
Yeah.
Which platform did we get in the exams and quizzes? On WebAssign or here?
Yes, now we don't know it. we will going to announce it later.
Okay.